introduction, and the genesis of change. SpaceX's groundbreaking decision to overhaul the Starship heat shield is detailed in a new report. The story begins in 2021 at SpaceX's Starbase facility in Texas, where engineers confronted the limitations of traditional ceramic heat shields. Initial test flights revealed concerning patterns in ceramic tile performance during atmospheric re-entry, highlighting potential weaknesses in the existing technology. Early data prompted SpaceX to seek alternative approaches to enhance the resilience of the spacecraft during demanding atmospheric conditions. The pursuit of a more robust thermal protection system has driven crucial advancements in the development of Starship. This marks a pivotal moment in spacecraft design and engineering. The ceramic failure and the need for innovation. Early Starship test flights exposed critical flaws in the ceramic tile heat shield system. High-speed camera footage documented numerous tiles detaching during re-entry, a worrying sign of structural instability. Telemetry data revealed escalating temperatures around crucial landing flaps, indicating potentially catastrophic overheating during descent. This highlighted a serious concern about the spacecraft's structural integrity and landing capabilities under high-temperature conditions. The consistent failure pattern prompted a thorough review and spurred the development of a new, more resilient approach to thermal protection. These early failures demonstrated the inadequacy of the current approach. The gamble and the dawn of a new material. Facing the ceramic tile failures, SpaceX took a bold step. Elon Musk proposed a radical shift to stainless steel heat shields, a departure from decades of aerospace tradition. This unconventional choice sparked an immediate debate among engineers. Intensive testing in SpaceX's metallurgy lab followed, focusing on the creation of alloys capable of withstanding extreme re-entry temperatures repeatedly. The key breakthrough came from a materials scientist with nuclear reactor expertise. This innovative approach sought to overcome the limitations of the existing ceramic-based system. The goal was to develop a material and system resilient enough to endure the rigors of multiple re-entries with minimal maintenance. The transpirational cooling system and Flight 6. Flight 6 served as a crucial test of the new metallic heat shield. Embedded among the standard ceramic tiles were experimental metallic panels with sensors. The launch proceeded as expected, but re-entry presented a nerve-wracking moment. High temperatures soared beyond 3,000 degrees Celsius, prompting intense monitoring in the control room. Early data showed the steel tiles survived the extreme heat, although some discoloration and warping were observed. This initial success, however, revealed a deeper need for the tiles to function as a cohesive, interconnected system, rather than isolated components. Analysis of the results highlighted the need for a more integrated approach to withstand the extreme forces. This realization refined the design considerations for the next iterations of the heat shield system. The data was promising, but also underscored the complexity of the problem and the need for further refinement. Fuel as a coolant and the cooling system challenge. Recognizing the need for an efficient cooling system, engineers explored the possibility of utilizing Starship's existing liquid methane propellant. This unconventional approach aimed to leverage the propellant's cryogenic temperatures for dual-purpose use. The challenge was enormous, precisely calibrating coolant flow to prevent fuel waste and catastrophic failure. Countless iterations and tests followed, pushing engineers to the limits. Each failure provided valuable data for refining the system, bringing them closer to a functional solution. The sheer complexity of the cooling system and the delicate balance required to avoid both under- and overcooling highlighted the demanding technical aspects of this innovative approach. This aspect of the project demonstrated the rigorous testing and refinement process integral to the development. Progress, challenges, and the future of Mars missions. The project's evolution yielded a more sophisticated heat shield design, featuring a complex honeycomb structure beneath each tile. This structure optimized coolant distribution, maintaining structural integrity under extreme conditions. Computer simulations suggested the system could withstand not only Earth's atmospheric re-entry, but also the even more demanding conditions of Mars' atmospheric entry. This was a significant advancement, potentially revolutionizing spacecraft maintenance and reusability. The traditional process of extensive inspections and replacements for ceramic tiles would be dramatically streamlined. The potential for rapid turnaround, landing, minimal inspection, and immediate relaunch posed a major leap in efficiency and reduced costs associated with spaceflight. This innovative approach held the key to overcoming previous limitations, the testing phase and continued innovation. Testing continued, with each prototype revealing crucial insights. Ship 35's development showcased the team's perseverance. engineers subjected a full-scale section of the heat shield to conditions exceeding real-world re-entry scenarios. The material's resilience was tested under intense heat, exceeding 3,500 degrees Fahrenheit. Astonishingly, the metal maintained structural integrity, displaying its remarkable heat resistance. These rigorous tests, pushing the boundaries of what's possible, provided crucial data about material performance under extreme conditions. Analysis of the tests informed further refinements in the heat shield design, critical for withstanding the challenging environments of both Earth and Mars. This commitment to thorough testing and analysis is essential to the ultimate success of the project. The transition and future. SpaceX's methodical approach to testing, highlighted by the continued use of ceramic tiles in some prototypes, while seemingly cautious, reflects a deep understanding of the challenges ahead. This data-gathering strategy ensures thorough analysis and refinement of the metallic heat shield alternative. The transition to the new system is expected to coincide with a key milestone, a successful recovery of a returning Starship. This upcoming event will be crucial in determining the viability and reliability of the innovative heat shield design. The next few months will be critical in demonstrating the system's readiness for demanding space missions. Each test flight and subsequent data analysis further solidifies the project's progress toward the goal of routine space travel and a sustainable presence beyond Earth. The road to Mars and beyond. SpaceX's ambitious Mars mission hinges on the success of the Starship, and the heat shield plays a critical role. The revolutionary metallic heat shield system, replacing traditional ceramics, promises to revolutionize spacecraft design and reusability. This promises a significant reduction in the cost and time associated with space missions. Recent discoveries, like vast underground caverns on Mars, suggest advantageous locations for future settlements. These findings, combined with the advanced heat shield technology, enhance the feasibility and efficiency of long-duration missions to the Red Planet. Starship, equipped with this cutting-edge thermal protection, stands as the primary vehicle for realizing this ambitious goal of human colonization. The success of the heat shield technology is integral to this monumental endeavor. The human element and ongoing challenges. The human element of the Mars mission is crucial. The selection of the first crew reflects a diverse team of astronauts, scientists, and engineers. Key individuals, like Dr. Sarah Chen and Mohammed Al-Rahman, possess specialized expertise relevant to Martian colonization. Their roles, including geological analysis and water recycling, underscore the significance of specialized skills in ensuring a sustainable human presence on Mars. The challenges faced during the 6-month voyage, such as a micrometeoroid impact, highlight the inherent risks associated with space travel and the critical need for robust design and engineering solutions. These challenges underscore the ongoing development and refinement needed for long-duration space missions. This part of the report emphasizes the importance of human ingenuity and resilience in space exploration. SpaceX to launches 131 spacecraft on Transporter 12 Falcon 9 rideshare mission from California. SpaceX launched 131 payloads Tuesday on board the company's 12th smallsat rideshare mission to date. The Transporter 12 mission flew on board a Falcon 9 rocket, lifting off from Pad 4E at Vandenberg Space Force Base at 11:09 a.m. PST, 2:09 p.m. EST, 1909 UTC. The Falcon 9 booster, used on Tuesday's flight, tail number B-DO88 in the SpaceX fleet, was launching for a second time. It previously launched the NROL-126 mission, which was a combination of 20 Starlink V2 mini-satellites and an undisclosed number of Starshield satellites for the National Reconnaissance Office. About 7.5 minutes after liftoff, BN-88 touched down at Landing Zone 4, located near the launch pad. It marked the 23rd booster landing at LZ-4 and the 397th booster landing to date. Of customers from around the world, from research institutes and aerospace companies to other government space agencies, like the United Arab Emirates Mohammed bin Rashid Space Center. The MBRSC's MBZ seat, an Earth observation satellite, is named after the country's president, Sheikh Mohammed bin Zayed Al Nahyan. The agency said the satellite is designed to process and transmit images within 2 hours to provide insights for applications such as environmental monitoring, disaster relief, and infrastructure management, enabling decision-makers to act swiftly and effectively. Other Earth-observing satellites include Planet Labs PBC's high-resolution Pelican 2 satellite, along with 36 of its superdoves. This Pelican satellite is designed to provide up to 40 centimeters class-resolution imagery across 6 multispectral bands optimized for cross-sensor analysis, Planet wrote in a pre-launch statement. Additionally, Planet has collaborated with NVIDIA to equip Pelican 2 with the NVIDIA on-orbit computing, with the aim of vastly reducing the time between data capture and value for customers. Also hitching a ride to space are Spire Global's 2 low-Earth multi-use receiver, LEMUR 3 satellites, along with 4 other satellites. The LEMUR 3 CubeSats are designed to help improve weather forecasting, maritime monitoring, and augment Internet of Things connectivity, according to the company. 2 LEMUR 3 satellites, developed in collaboration with Myriota, will expand global IoT coverage with cutting-edge direct-to-orbit communications, enabling Myriota's IoT solutions to operate seamlessly and more effectively, Spire said in a pre-launch statement. This network will enhance connectivity for critical sectors such as agriculture, defense, and logistics across regions like the US, Europe, and Latin America, promoting sustainability and efficient resource management. Spire's satellites are among the 35 satellites being flown by Satellite Deployment and Hosting Company, was a landmark mission for us. And as we look ahead to Transporter 12, we're excited to keep the momentum going, said Robert Sproles, ExoLaunch CEO, in a pre-launch statement. We deeply appreciate the trust our customers place in us and extend our thanks to SpaceX for their outstanding support. Our long-standing partnership with SpaceX has been a cornerstone of ExoLaunch's growth, and it's an honor to be part of every transporter mission. Satellite deployment began about 54 minutes after liftoff, with the deployment of the GSAT and Gen 1 satellites by ExoLaunch, and concluded more than 2 hours and 22 minutes after liftoff with the deployment of Firefly 2 by Pixel.